Okay, so we continue with our discussion on noise in angle modulation systems. Since it has been quite some time, a few days now since we discussed it last, let's recap the basic principle on which we are going to do this analysis. If you recollect, we decided to draw a phasor diagram of the signal plus noise. In this case, your received signal at the output of the band pass filter at the receiver is the sum of the desired PM signal plus the narrowband noise or band pass noise, right, n sub I t, which you can write like this, where E sub n t denotes the envelope of the noise and theta sub n t denotes the instantaneous phase of the noise process, right. So, we look at the sum of these two signals, and that comes in the form of this phasor diagram. This phasor represents the signal, the modulated signal, the angle modulated signal, this angle being equal to omega c t plus psi of t, right. This phasor represents the noise with an amplitude of E n t and an angle with reference to the reference phasor of omega c t plus theta n t, right. And therefore, the resultant phasor that you see y I t has this resultant envelope. This is the envelope of the resultant phasor, a resultant signal, and the total angle that you will see will be omega c t plus psi t plus delta psi t, right. And that is what, therefore, we can write this signal also as equal to this signal, where R t is this phasor and delta psi t is this angle. Okay. I think this does not require much explanation, but if you have any questions, we can discuss it now. Is it okay? Can we start from here? And then we proceed a little further and try to write an expression for delta psi t, right, in terms of the quantities indicated here. You notice that this angle is theta n t minus psi t, right, that is this angle minus this angle from this triangle, all right. Then, having figured it out that this angle is theta n t minus psi t and making the assumption of small noise, which is the case we are considering first. The small noise case would essentially correspond to the situation where the length of this phasor is much smaller than the length of this phasor, right. So that you can consider, actually the scales are not appropriate in the figure that I have shown. If this is really true, you can more or less assume that these two lines are going to be in parallel, because they are very far removed from the origin, and therefore, these two angles are nearly equal, and therefore, you can write an expression for this length, this perpendicular from, or this arc you can say from the point A to this resultant phasor as the sine of this phasor times E n t, right, which is what we had discussed last time. This is where we are assuming that delta psi t is very small, which will be the case when E n t is much less than the carrier amplitude. We can write an expression for delta psi t as equal to E n t sin theta n t minus psi t, which is essentially the length of this arc, right, E n t into sine of this angle, which is this angle, upon the radius. You can approximate the angle by arc length upon the radius, which is what we have done here. So, this is the arc length, the numerator is the arc length divided by the radius, which is a. So, you can approximate delta psi t by this angle. Okay. That is a very standard thing that you do, right. So, this is now the this becomes our basis for further discussion. So, what can we say about the demodulator output now? What will be our demodulator output like? V naught y naught t. Remember what is the input to the demodulator input? What is the input here to the demodulator? It is this signal, and an ideal phase demodulator, what will it do? It will produce an output which is proportional to the instantaneous phase deviation, right. So, it will produce an output which is psi t plus delta psi t. So, assuming that you have an ideal phase demodulator, the output of this demodulator would be psi of t plus delta psi t, whereas the desired output would have been psi of t. If you remember, psi of t is your k sub p times the message waveform mt, and delta psi t, we just figured this out, was E n t upon a into sine of this angle, right. This is the desired output, this is the contribution of noise. Okay. Now, the analysis is on the face of it still complicated, because the noise term also contains the signal term, right. So, that is why it is a nonlinear system, its analysis, exact analysis is very difficult. However, we can now make that approximation or that simplification that I talked about last time. Look at the comparison between theta nt and psi t. Both of them are phase terms, but theta nt is a noise, the phase component of the noise process. Psi of t is a phase component of the signal, modulated signal process. Modulated signal has a bandwidth of b. So, psi of t has a bandwidth of b, but theta nt has a bandwidth of much larger, it is 2 delta f plus 2b, is not it. Theta nt is coming from the noise, right. These are the low pass components, envelope and noise, envelope and phase of the band pass noise process, and this band pass noise process is coming out of a band pass filter whose bandwidth must be equal to 2 delta f plus 2b, right. So, the bandwidth of the baseband signals E n t and theta n t have a much larger bandwidth, as I discussed last time. What does it mean? Is this point okay? Can we concede this point, that these two signals, these two envelope, this envelope and this phase have much larger bandwidth than psi of t, and therefore, the consequence of that is that the rate of variation of theta n t will be much larger than the rate of variation of psi t, right. The fluctuations in theta n t will happen at a much faster rate than they will happen in the phase psi of t, which means that if I were to do the analysis of this output over a relatively short period of time, you can consider over that period of time psi of t remaining nearly constant, whereas theta n t goes through a lot of fluctuations, right. Let us assume that, let us do the analysis as if you are doing the analysis for a short period of time, comparatively short period of time, not infinite time, but comparatively short period of time, and of course, you can extend the argument on period to period basis. So, if you make this assumption, or rather which is really true, since psi of t varies much more slowly than theta n t, theta sub n t, we can assume that psi of n t is nearly constant over the period of consideration, is equal to some value, constant value equal to psi. Is that okay? So, what can we say about delta psi t in this case? We can write this as E sub n t upon a into sine of theta n t minus psi. How does it help? How does doing this approximation help? Basically, I am trying to get rid of the dependence on the signal. This noise part, this is output noise, delta psi t is kind of output noise that you will see. I want to express it purely in terms of noise properties if possible. So, the simplification I make use of is this, that whereas this fluctuates much faster, this remains constant over a certain period of time, right. Are you comfortable with this point that I am making here? Okay, if that is the case, let's just expand this using trigonometric identities. We can write this as sin theta nt into cosine psi minus E nt upon a cos theta nt into sin psi. Yes, please.
So when you are ignoring the variation of psi t itself, then how can you consider delta psi t?
Delta psi t is a wideband process because theta nt is a wideband process.
So previously just write it and what is the bandwidth of theta and t?
Oh, this I discussed last time, maybe you have forgotten. Okay, let's go back to this issue. Your signal has this phase psi of t, right? Noise is this. Okay, this is a noise process. What I am saying is this noise process is the noise process which is being seen at the output of the band pass filter at the receiver. That band pass filter must have a bandwidth equal to the bandwidth of the FM signal, isn't it? If that band pass filter does not have a bandwidth equal to the bandwidth of the FM signal, you would not allow the FM signal to come, a PM signal to come through, right? So the band pass filter preceding the demodulator is a filter with this bandwidth, and therefore the noise process which was right at the input to this filter would now be if band pass process whose bandwidth is this. That means both ENT and theta nt are low pass processes whose bandwidth is delta plus B. This is a point I explained in detail last time, so I thought of not repeating it today, but since you have forgotten it, this is the reason. Because our demodulator is preceded by a band pass filter which must have sufficient bandwidth to allow the desired signal to come through, which has a bandwidth of 2 delta plus B. Is that clear? Therefore, this fluctuates much faster than this, right? This also means that delta psi t fluctuates much faster than psi, because delta psi t depends on theta nt, right? Is that okay? Okay. So now let's look at this. What is ENT into sin theta nt? That is nothing but NCT, the in-phase component of noise in the band pass representation, right? So this is NCT upon A into cosine psi, and similarly what is ENT? Sorry, this is NS, right? And this will be NC into sin psi. Okay. Now, do you remember the characterization of NST and NCT in terms of NIT? What is N? What are the NS and NI? Let's recap. Here, the band pass process, noise process at the input of the input of the demodulator is NCT cosine theta nt. No, sorry, omega CT, cosine omega CT minus NST sin omega CT, right? This is the representation of the band pass noise process, which can also be represented as ENT into cosine of omega CT plus theta nt, right? Now, what is the characterization of these two quadrature components in terms of this? Let's say in terms of power spectral density. The power this is a band pass process whose height will be n by 2 from, okay, let me plot it. NIT would have this kind of power spectrum. Do you agree with this? Around FC it will have a bandwidth of twice delta F plus B, right? It's going outside this region, so let me put it like this. And the height is n by 2. Okay. What can I say? So this is the spectrum of Ni. What can I say about the spectrum of NCT and NST? They are low pass processes whose spectrum would be n from minus delta f plus b to delta f plus b, and height is n, because the two components must have the same variance as this, right. So, the height gets kept. Is it clear? So, this is the power spectrum of NCT as also the power spectrum of NST. So, these are the power spectral density functions of the two quadrature components in terms of the power spectral density function of the band pass noise process. Okay. So, if you were to write this down, suppose I were to look at this expression, think of delta psi t as the output noise process, a random process, output noise process. It is a linear sum of two noise processes, right. What can I say about the power spectral density of this process, assuming that NC and NS are uncorrelated, which they are, right. The quadrature components of noise, band pass noise, are uncorrelated. So, what will be the power spectral density of this? The autocorrelation function of this would be the autocorrelation function of this plus the autocorrelation function of this, right, because the cross correlation is 0, right, and therefore, the power spectral density would be the power spectral density of this part plus the power spectral density of this part. So, which will be essentially this coefficient square times the power spectral density function of this plus this coefficient square times the power spectral density for this, right. So, you can write S delta psi t f I will just simply say S delta psi f will be cosine square psi upon a square S n s omega plus sine square psi upon a square into S n c omega, right, and that is nothing but cosine square. Since these two are equal, these two are same, they can be factored out and you will be left with essentially any one of them upon a square, and cleverly like this we have removed the dependence on psi, right. Of course, there is some assumption involved here that we are doing this analysis for a fixed period of time over which psi remains constant, but noise process fluctuates. Is it okay? So, that is what we can say about the power spectral density function of the output noise in terms of the power spectral density function of the input noise. So, if I were to expand this further, this reduces to S delta psi f equal to n by a square, right, for mod of f less than delta f plus k plus b, right, is equal to 0 for f let us say otherwise, right. I am just substituting for the fact that S delta SNC or SNSF is equal to n from minus delta f plus b to delta f plus b, which is what I read. So, interestingly, the output noise process has the same power spectrum shape, but its height is much lower. It is lower by an amount equal to a square, the amplitude of the carrier, right, and that is a very interesting phenomenon. We will come back to this. So, if you were to now go back to the calculation of noise power, now what do we need to consider further? This is the power spectral density function as seen at the demodulator output, right. Demodulator output contains two parts, the signal part and the noise part, right. But we are not going to look at this is not the total output noise. Can you see that? Because you see, so far the demodulator was working on a signal whose bandwidth was delta f plus b or twice delta f plus b, but my signal of interest has a bandwidth only of b. So, at the demodulator output I can have a filter whose bandwidth is only b. I do not have to look at this entire noise process. this is the power of delta, the power spectral density function of delta psi t. But my receiver would have this. If you go back to the block diagram I drew that day, you have this band pass filter whose bandwidth is twice delta f plus p. This will be followed by a phase demodulator, and we are looking at delta psi t at this point, and this delta psi t has a bandwidth of delta f plus p. But as far as the signal part in the demodulator output is concerned, that has a bandwidth only of b. So, I do not have to look at this entire noise process. I must therefore pass this through a low pass filter whose bandwidth is b. So, the final output noise process that you will see here will have bandwidth only of b, and so the noise power that will be contributed by the noise process delta psi t will be the one which lies in the bandwidth from minus p to plus p, right. So, we can say if I consider this noise process here as NOT, then the power spectral density of this noise process will be the same as this n by a square, but not over delta f plus b, over simply b. Right, that is delta f greater than b. Okay. So, what is the total noise output power? It will be 2b into n by a square, which is 2 nb upon a square. What is the output signal power here? What is the output message that you will get here? Kp times mt. If the phase demodulator is perfect, right? So, the signal power would be k sub p square into m square bar, and therefore, your output SNR S naught upon n naught will be a k sub p whole square into m square bar upon 2 nb. All right. Now, I must do the final job of expressing this in terms of input signal to noise ratio in the message bandwidth. So, let us look at what is the input signal power in this case. What is the nature of the input signal? Just the signal component. It is a cosine omega ct plus psi t. What is its power? A square by 2, right. So, S sub I is simply a square by 2, which implies that S sub I upon nb, which is the value of gamma. If you remember, gamma is defined as S sub I upon nb, the input signal to noise ratio in the message bandwidth, right. That is going to be equal to a square upon 2 nb.
So, but the NI has a larger bandwidth.
Sorry?
So, NI will have a larger bandwidth.
No. This has nothing to do with NI. Gamma, if you remember, the definition of gamma is it is a benchmark parameter which is defined as the input signal power upon input noise power in the message bandwidth, not the incoming signal bandwidth, because this is the benchmark for comparison. How much, see, why this benchmark? This benchmark because the noise that is present in the message bandwidth is what you cannot get rid of ever, right. That is why for all EM systems the output SNR was equal to gamma itself, right. So, this is going to be a universal benchmark for comparison. We like to always express the output SNR in terms of gamma, right. So, gamma is what you could have got anyway by using a simple modulation scheme like EM, or by just not using any modulation scheme, right. For example, if you had transmitted the signal at baseband itself, this is the output SNR you would have got. I am comparing with that, right. Always the benchmark is the figure of merit with which you are going to compare is this particular one. So, in this case SI by NB will be equal to a square by 2 NB. You agree with this? Any questions on this? So let us now express this S naught by N naught in terms of gamma. So if I combine these two expressions, what can I write? S naught upon N naught is equal to A square will cancel off, so we will be left with Kp square M square bar into gamma. So this is the key expression. Let me write it separately, so that this makes an impact on you. Okay. To see the impact of this expression and how it compares with what we have discussed earlier, let us do some more calculations, very simple calculations. Let us try to express this M square bar in terms of standard parameters in which we describe angular modulated signals. What are the parameters in terms of which we describe angular modulated signals? In terms of peak frequency deviation, for example, right? So let us write in terms of peak frequency deviation rather than M square bar, which is a slightly unknown entity here. So in the case of phase modulation, what can I say about peak frequency deviation, delta omega or delta f? The instantaneous value of the phase is equal to Kp times mt. What is the instantaneous value of the frequency deviation? It will be Kp times derivative of mt, right? So what is the peak frequency deviation going to depend on? It is going to depend on the peak value of the derivative of the signal, right? So I can write delta omega at the peak frequency deviation. So this is the peak frequency deviation, peak, in this case angular frequency deviation. This is going to be equal to k sub p times, let me denote by mp prime as the peak value of the derivative, right? So let me make it very clear. mp prime here denotes, if you look at m dot t, the message waveform, you are looking at its maximum value. Is that okay? That I am defining as mp prime square, mp prime. So now let us substitute for what is delta omega? Okay, substitute for Kp from here. So we get S naught by N naught as equal to delta omega whole square into M square bar upon MP square, MP prime square into gamma. Now let us look at this expression. This expression is very informative because this is in terms of a parameter of the modulated signal, which is the peak frequency deviation. This is a parameter of the message signal, the mean square value, the ratio of the mean square value of the message signal to the square of the peak derivative, maximum derivative. It is some property of the message signal. It is going to be some constant value for a given kind of signal, right? So we can think of this as some constant value which depends only on the message signal, kind of message signal you have. For example, if it is a tone modulation, you can calculate what this value will be. It is going to be some fixed value, and this is the input SNR in the message bandwidth, the benchmark against which we are comparing every modulation scheme. So what do we find? We find that the output SNR is proportional to, if you forget about this constant, delta omega square, the peak frequency deviation, right? And the larger the peak frequency deviation, the better the output SNR, right? You see that? That means that, let us say if I double my frequency deviation from some existing value, my output SNR will increase by 4 times. In terms of decibels, 4 times is 6 decibels, right? 10 log of 4 is 6. So every doubling of the peak frequency deviation is going to improve my output SNR with respect to the input SNR by an additional 6 dBs, right? So this is a very, very important parameter to note. So SNR increases And delta omega in some sense is a measure of the bandwidth of the FM signal, isn't it? Because actual bandwidth is delta omega plus 2 pi b or delta f plus b. So, if you assume that b is much smaller than delta f, so delta f is a measure of the bandwidth in some sense, right. So, the larger the bandwidth of your phase modulated signal, the larger the improvement or the better the output SNR, right. So, that is the key result here. So, SNR increases in proportion to square of the transmission bandwidth. This is the key result. There is a 6 dB increase in output SNR for every doubling of bandwidth. Okay. Now, where did this benefit come from? Why did this happen? So, basically what we are saying is wideband phase modulation would be much superior to either our baseband transmission or AM transmission, right. What is this improvement due to? Can you see that? Can you visualize that? If you go through the steps of our analysis, which particular step leads to this great improvement in output SNR? I suggest that you look at the steps that I gave you in connection with the phasor diagram, right. Go back to this expression, this phasor diagram. This is a phasor diagram of the signal plus noise process, and the important point is delta psi t. This is the output noise, and that is this expression. It is this division of by A which causes this whole improvement. The larger the amplitude of the carrier with respect to noise, that is when you are working with the small noise condition, the smaller the effect of noise on delta psi t, right. It is like this. Your noise is additive. Let us go back to this expression. This noise is additive. This noise will affect the amplitude significantly, can affect the amplitude significantly, right. But the effect of this noise, as long as this noise is not too large, on phase of the signal is going to be much smaller. And fortunately for you, the phase demodulator will look at the phase and not the amplitude. In fact, we are going to have a limiter, bandpass limiter, not just a bandpass filter, a bandpass limiter at the input of the demodulator. So, it will be totally insensitive to the amplitude variations. It will be only sensitive to the phase variations, and the phase variation is scaled down by the factor of A, right, and that is what causes the spectral density to come by to be multiplied by 1 by A square and things like that, right, n by A square instead of n. That is a crucial factor. The spectral density is not n over the bandwidth of interest, it is n by A square over the bandwidth of interest, and that is what causes the reduction in the noise. Basically, the phase of the signal is much less sensitive to the noise process than the amplitude of the signal, and you are killing amplitude variations, and your phase demodulator is only sensitive to the phase variations, and that is what causes in the. So, that is the reason why the FM and PM signals are much superior in performance to AM signal, right, because of this direct there is a trade-off, of course. If you want more improvement in the SNR, you have to use more bandwidth. In fact, this is the conventional wisdom of communication engineers. You want better SNR, you must pay a price in terms of bandwidth. Okay. This picture has changed slightly over the recent years, but this conventional wisdom generally holds. If you do some clever things, you can make this trade-off better, but generally this trade-off always exists. Improved SNR will come at the cost of bandwidth. Okay. We will discuss more examples of this as we go along. Okay. So, that is as far as phase modulation is concerned. Let us now turn to frequency modulation. How do things change now?
Sir,
Yes, please.
so this is just a small noise case. What happened in this large?
We will come to the large noise case separately. Right. Let me complete the small noise analysis both for PM as well as for FM, and then I will discuss the large noise case. Right. Now, the entire analysis that I did for PM is more or less directly valid for FM. If you recollect that you can think of the FM modulator in terms of the PM modulator and the FM demodulator in terms of the PM demodulator. Right. So, you have to only do minor changes in the analysis to draw the required conclusions. So, if you recollect that I can have a message empty, first integrate it and then pass it through a phase modulator. Remember this? That is equivalent to my frequency modulation. Right. Then you have noise, and then you have a phase modulation, phase demodulator or phase modulation receiver, which will have the necessary band pass filter, band pass limiter in front of it, and this should be followed by d by dt, right, and that will be followed by low pass filter, etc. So, you can think of that low pass filter part of this receiver, right. So, just following up the phase demodulator receiver by a differentiator and preceding the phase modulator by an integrator, and that is your FM system rather than the PM system. So, I do not have to repeat the arguments, I directly write the output signal power here and the output noise power. Can we do that? What can I say about the output signal power? It will be obviously equal to kf square m square bar. I do not think I have to repeat that argument. This is your frequency demodulator, this entire thing. This will produce an output which is proportional to kf mt, right. So, the output signal power is kf square into m square bar. What about the output noise? So, to look at that, let us look at the power spectral density. Remember what was the nature of the power spectral density at this point? It was the power spectral density at this point of noise was like this, right. Between minus b to plus b, it was constant equal to n by a square. Is that okay? If you recollect this, that is the power spectral density function of noise at the input at the output of the low pass filter, at the input of the low pass filter, right, and therefore the output of the low pass filter had the total noise power, which was the area under this, which was n by a square into 2b. But now you are passing this through d by dt. So, what will happen to this noise power spectral density? And this is followed by a low pass filter, let us say, right. Or low pass filter can be anywhere, it does not really make a difference. So, what will happen to the power spectral density here? It will get multiplied by the transfer function of this differentiator. What is the transfer function of a differentiator? J omega, magnitude square of that transfer function. Power spectral density function gets modified by the magnitude square. So, it will get multiplied with mod of delta omega square or mod of delta f square. So, what will it look like? So, the power spectral density function will be as follows: S naught omega, S sub n naught omega will be equal to n by a square times omega square for omega less than or equal to 2 pi b, will be equal to 0 for omega greater than 2 pi b, right. Is that okay? Same thing, but multiplied with omega square or f square, depending on whether you are writing f. So, it will look like that. Instead of looking flat over minus b to plus b, it look like a parabola, right. And what is the output noise power that you will see? It will be the area under this power spectral density function, right. So, your output noise power n naught is So, it will be twice of the integral from 0 to b of n by a square into 2 pi f whole square df. And if you were to calculate this, this turns out to be 8 pi square into n b cube upon 3a square. This integration is straightforward. Combine the expression for S sub O and N sub O. You can write the expression for S sub signal to noise ratio of the output for the case of FM. Can I just write it down rather than looking at the details? This turns out to be kf square into m square bar upon 2 pi b whole square into, I am skipping a few steps so that we can directly write it in terms of gamma. Okay, and that is 3 times kf square m square bar upon 2 pi b whole square into gamma. Okay. Again, to write it in the standard form, I don't want to write it in terms of kf like I did for the case of PM. I substituted for kp in terms of delta omega, the peak frequency deviation. Right. Similarly, I substitute for kf in terms of the peak frequency deviation, because that's the measure of the bandwidth. Right. So, directly writing the expression in terms of the bandwidth parameter is more convenient. So, now what can we say about delta omega, the peak frequency deviation? It will be kf times simply mp, not mp prime. mp prime was the peak value of the derivative of the message signal. In this case, the peak frequency deviation will depend on the peak value of the signal itself, isn't it? Because in an FM signal, instantaneous frequency deviation is proportional to the amplitude of the message signal. It is equal to kf times mt. Okay, let it be like this, factor of 2 pi. If you need to adjust, you please adjust yourself. Right. So, what we can say is that S naught by N naught, if I make the substitution, will turn to be 3 times delta f upon b whole square into m square bar upon mp square into gamma. By and large, a very similar expression. The details are slightly different. Instead of m square bar upon mp prime square, you have m square bar upon mp square. It is some other constant of the message signal, right? But this factor depends only on the message signal. Instead of depending only on delta omega square, it depends on delta f upon b whole square, right? Which is actually, if you think about it, something very similar to the beta parameter beta. So that is the expression that you have. But by and large, the same conclusion is valid, that every doubling of the bandwidth will produce a 6 dB improvement in the output SNR, right. The detailed expression is slightly different, the actual values are slightly different, which means that there is a relevant question that you can ask here, that for a given message signal, whether FM is superior or PM is superior, right. That will depend on the kind of message signal you have. You cannot draw a general conclusion, because that will depend on the value of these constants, right. So, depending on how these constants change, either FM or PM will be superior. So, let us just do a small comparison between these two. Any questions so far? Let me write down the ratio of these two expressions. for the phase modulation case and for the frequency modulation case, output SNRs in the two cases. You have the two expressions, you just divide one by the other and simplify. The gamma squares will cancel off, the delta f square will cancel off, right, and what you will be left with will be parameters of the message itself. Everything else will go, isn't it? Delta f will go, gamma will go, only message parameters will remain, right. So that gives you some idea of how it depends on. So this will become right. Now if you want to say to find out which one is superior, you just look at this ratio. If for a given message signal this is greater than 1, right, PM will be superior. If this is less than 1, FM will be superior, right. So let us say if 2 pi b square MP square is greater than 3 MP prime square, then we say PM is superior, otherwise FM is superior, right. So I do not know whether you can convert this into some kind of physical picture. Very gross physical picture can be constructed if you understand what is the meaning of MP prime. MP prime, if you remember, was the derivative, the peak derivative of the message signal, right. So if this value is small, right, then you can expect PM to be better, right. What does it mean? Essentially it means that if most of your spectrum of the message signal is concentrated at lower frequencies, right, because in some sense the derivative will be large if the high frequency components are large, right. Just think about it. This is some kind of physical picture I am giving. So if your bandwidth is large, you can expect large variations, right. Bandwidth large means large fluctuations. Large fluctuations means a larger derivative, right, some way or the other. So generally that's a very gross physical picture. I am not trying to make it very precise. So generally if most of your spectrum of the message signal is concentrated at low frequencies, you can expect PM to be performing better. If on the other hand the spectrum is more concentrated at higher frequencies, FM will be better, right, something like that. It's a very gross picture. And that is why in practice one does not either use pure FM or pure PM. Remember I talked about some pre-emphasis and de-emphasis earlier. One tries to optimize the performance in that sense, right, for the message signal.